recording started? Yeah, okay, cool. This is 31 minutes past the hour. We're gonna start. Welcome everybody. This is our 11th Hackaday session on quantum computing. And for new communities joining us 2 weeks ago, that's the third session. And for people who are new today, this is where we post everything, all the information and the class. I update with comics every week. So on Hackaday comics introduction to quantum computing, you will find all of the recordings from past sessions. Every Sunday we meet for 30 to 1 hour. Usually I try to keep it within 30 minutes to discuss a concept. And then we can answer some questions and do some discussions after that. We also use the Q-Sharp documentation on the Microsoft documentation website and the quantum katas for our coding exercise. Last class and 2 classes ago, we discussed superposition. And this picture shows you kind of a landscape for learning quantum computing. You can go pretty far with the Q-Sharp exercises, learning the concepts, and go to all these linear algebra or algorithms that you can express using the quantum language Q-Sharp. So today we're going to discuss this very exciting and interesting subject, interference. And that's built onto what we learned so far. So mainly superposition concepts. For people who have been to this Hackaday classes, this will be a revision, but I will also show you some of the new pages and talk a little bit about physics too. Just a step back, looking at what we discovered 2 classes in the past 2 classes, the quantum bits and superposition. So you should know that a qubit can be expressed as a vector, which in turn is also a superposition of these 2 states, 0 or 1. Each of them would have an amplitude associated with them, telling you how much of the 0 and 1 are in the system. All you need is that you will have this normalization condition where no matter how many states you have in your system, their amplitude squared needs to be add up to 1. So some examples like how you can use a metaphor to express qubits. You could have probabilities of 1/3 and 2/3 coexisting, and you can have probabilities of mixed colored beads or spinning coins with half and half probability of landing on head or tails. So this amplitude square means probability of each state. And when you have multiple qubits, you would just add all of them up. That's why it's called superposition, which is also a linear combination of these different states. Each of them will have these amplitudes, and you just time them, square them, and add up to 1. As you grow your qubits, number of qubits, the possible states that could be in your system grows. When you have lots of qubits, you would not just keep writing all the outcomes. You would just use a summation to say that I will sum up all of the possible configurations in my system, and each of them with an amplitude. We mentioned that the amplitude can be any number. It could be real numbers like 1 to 1/2, 1/3. They could be negative numbers, but they could also be imaginary numbers. So in general, they can be complex numbers. The amplitudes can take all these different phases, the forms. So then some people, I'm really glad that Olivia, I think that is who asked on Hackaday comments. So if we want to have amplitude square equal to probability, how do we deal with the case when you have a imaginary number? You have this I here. I'm really glad that she asked that. So we will take a look today. how do you express complex numbers? This you have also seen in the last class when we wanted to show a qubit as in a three-dimensional space. But we're not talking about qubit right now. We're talking about complex numbers. When you have just real number, you can express it in a line. And the length of that just indicates how big your number is. But then when you have complex numbers, you give it a vertical axis. Then you can express a complex number as an arrow in a two-dimensional space. This we have seen last time. And you also see that it will have a length. It will also have a phase if you are measuring its relative position away from the x-axis. So I show in this new page here, you can actually express your complex number in two ways. One is with this Cartesian coordinates, so x and y, and you have these a and b. So real number is in your x-axis and imaginary number is your vertical axis. So where this arrow is basically expressed as these projection onto these two axes, a and b. But you can also write it in this polar coordinate, which has a length r and a phase phi. You can express r and phi in terms of a and b and the angle in this diagram. And you will see that when you're trying to calculate the amplitude, you're actually doing a modular square. So is absolute value square. But then you also quickly see that because this phase here, when you do a square, is doing a cancellation. So it cancels itself out. What it leaves is just the magnitude squared. So basically, if you have any amplitude, which can be your quantum state, then its probability is just the magnitude squared. You don't have to use a polar coordinate to calculate this. You can also just use a and b and see, oh, actually r is always positive, and squaring that you get a positive number. So probability can never be a negative number. That's that. And then what's the significance of having complex or negative amplitudes? From our daily experience, we have seen a lot of different kinds of waves. We have sound waves, light waves, water waves. That's in our everyday experience. We already know that if you have some wave, two waves having amplitudes in phase, so they would sync up and add up. So the amplitude overall will grow. But there are also cases where they can be out of sync and they would subtract each other and you get nothing. We know that amplitudes can add up, which is called a constructive interference, or amplitudes can cancel each other out. This is a destructive interference. So this happens in our quantum mechanical system. And in quantum computing, that's actually what we deal with. Because we can express our qubits with the amplitudes, then there must be interference going on in our qubit systems. So in quantum computing, we deal with probabilities. But classically, we deal with absolute numbers. So if you now use that interference argument and to look at our systems again, mapping your way of understanding in terms of these tree diagrams. This is what we learned as kids, like how do we calculate probability? Classically, if you want to know, say, tomorrow has equal probability of getting a sunny day or a rainy day, what is the probability of the day after tomorrow being sunny? If we were in a classical system, then we would just add up the probabilities. So we need to first time down the tree, and we time all of these possible outcomes being sunny. So 50% times 30% plus 50% times 90%. These numbers are just made up, just any number, but probability, they're always positive. So you get a 60% case in a classical system. But if you want to solve this in a quantum system, or if your system is quantum, there's no reason we cannot give your system a minus sign. And what that does is I just arbitrarily put a minus there. And because we're dealing with amplitude, we will label the amplitude the square root of the probabilities. And I can arbitrarily put a minus sign there. What that does is, even though you have an extra path to get a sunny day, that negative sign actually can subtract and reduce your probability of having a sunny day. This is what's really weird about quantum system, is that even if you have more ways to get to where you are, it could play a negative role. So this example turns out to give you 8% of getting a sunny day. This is what happens when you want to do a measurement on your system, is the amplitude that does the constructive and destructive interference that leads to your result. So if you're observing certain results in a quantum system, that means that that particular result, before you measure it, it would have constructive amplitudes all adding their probabilities up. So the other possible outcomes are eliminated by those destructive interference. That's why you do not measure those unlikely results. And that's what we get in measurements. To have a little bit more, to read a bit more formal description of that classical and quantum probability theory, Scott Aronson has given quite a lot of interesting write-ups and lectures in his own works. So I recommend you to look it up. And it is called a 1 norm for the classical case and 2 norm for the quantum mechanical case. So we will not go into too much depth here, but the point here is that we are dealing with amplitudes in quantum systems, and the amplitudes can be positive, negative, or even complex. And that's what leads to interference as well as measurements. It's not just something that we cannot observe because quantum mechanical systems typically are in very small scale and very cold, but there are actually measurements that we have observed that's directly expressing this interference. For example, this double-slit experiment that is very famous. You probably heard of it sometime in your study. There, you can create an experiment that you would have 2 slits letting electron beams to go through. And we know electrons are intrinsically quantum mechanical particles. They would behave in a quantum way. If you close one of the slits, you would get this distribution that most of the electrons would appear close to the slit in the center. And you would think in a classical way, if this slit gets open, then you probably would see 2 peaks like this. But that's not what happens. What happens is that these 2 beams will interfere with each other. And it could even have these destructive interference very close to where the slits are. And you see a dip. And in the center where they have constructive interference, you will see most electrons. That's really cool. That is a direct manifestation of quantum interference. And we conducted an experiment to discover this. Whenever you have a qubit, a quantum system, when you're doing a measurement, you're actually observing this interference effect. And measurements are not reversible. Like our previous metaphor, if you had a spinning coin, you wouldn't know which side it will land on, and the measurement is kind of knocking it down and doing a measurement. Once it lands down, it would not be able to reverse back. So that's what happens. Say you have a quantum system with 2 qubits, and you have these 4 different possible states. Each of them has an amplitude describing them. Then if you do a measurement, measure the first qubit, and find out that it is 0, that means it will be these 2 states that's contributing. So you kind of eliminated these 2. And you know that the probability of having the first qubit to be 0 will be the C00 squared plus C01 squared. And after this measurement, you haven't done anything to the second qubit yet. You would then come to a new quantum state that would be these 2 possible states adding up. And you have to keep the probability sum to 1. That's why there is a square root of p now to normalize your system. So this is what happens after you measure the first qubit. If you then measure the second qubit, then it would be either 0 or 1. So if your outcome is 0, then it will be this state that is contributing to your measurement. And you would know the probability will be calculated from the C00. That's what measurement is. And we should do some exercises. We have a very good exercise already that makes a quantum random number generator. So think about the qubits are actually intrinsically random number generators, because if you have a qubit with unknown amplitudes, you can do measurements. And if you have like a fair coin, it can land on either head or tail. So if you have a qubit that can either come out as 0 or 1 with unknown probability, you just keep measuring it. So every time a random 0 or a 1 will come out. That's an intrinsic random number generator. So we actually have an exercise on this on the MS Learn, Microsoft Learn website. Go there, take this class at your own pace. This is a very, very interesting, very fun project that also teaches you how to set up your computer's environment and write Q-sharp programs using the quantum development kit. So we would not use our class time to do this. So, but then this link is here is for you to run it on your own. But today we're going to do this exercise on the quantum katas. There's no installation needed for people who have not done this before. The quantum katas is a series of exercises written in Q#. It's on github.com Microsoft/quantum katas. Let me see if someone can post the link here, that could help. I can also do that. Yeah. And what we're going to do today is to use the measurements exercise. You should all go onto your own browser and open this up and open the measurements exercise. It lets you run this kata directly on the Jupyter Notebook online, so no installation. But as Barry pointed out, is if you want to save your answers and everything, you can download it and run it locally on your own computer. You can run it using Jupyter Notebook, or you can also use the Quantum Development Kit. If you go through this Microsoft Learn course, then you can also use this QDK to download the Kelowna katas and run it there. We're just gonna do it on the browser. Make sure you read the words if you're doing this by yourself, but we're just gonna directly jump to running the packages. This is just letting your environment to set up and load all of the library that is needed to do this. Seems a little slow on my computer. I don't know if you guys have this loaded up quickly. There are quite a bunch of libraries for this to load up. Well, let's just take a look. Yeah, now it's good. So you see all these packages got started. The first exercise, very simple. It actually tries to help you by giving you the instructions. If you have a qubit that is guaranteed to be in 0 or 1, let the output be true if it was in the 1 state, or false if it was in the 0 state. This is kind of teaching you a way to let you write return. So it's already telling you to just do a return, and the measurements, the syntax for the gate is not a gate, but operation measurement is nothing but AM. It's very intuitive. So this would let you return the result and give, it would be a true because your equal is to 1, false if it's 0. So this should be correct and it should run as successful if everything goes okay. Otherwise, I need to reload the page. Let's move on to the next exercise and let this one run by itself. Now you have a qubit in an arbitrary state, and then change the state of the qubit to 0. How do you do this one? So your qubit could either be 0 or 1. So what you need to know is if your qubit is in 0 or 1, and telling it, so if it's 0, you do a measurement. If it's 0, then you don't have to do anything. But if you do a measurement and find out it is 1, you can change it to 0 by doing a flip. And we learned how a flip gate works last time. If people remember that, you can shout in the chat. So I might have to reload my page because this one was not running. I had this problem earlier, but reloading worked. Yeah, some people are saying the words are too small. You can do a Control Plus or whatever you use to zoom on Mac on Teams. So I've already increased the words here. I don't know why this is so slow. It's okay. We're gonna use the same thing, this thing that we just learned. So we're gonna do an if statement. This is exactly, Q# is really high level, and you can also write classical code within Q#. So the logic is as what you would think it would be. So if it is 1, then you make the flip. So this should do. I don't know, my screen is really slow. So if you guys type in this, you should see a success showing up if your browser is working okay. Now, task 3, it gets a little more interesting. Your starting states are now plus or minus. So just as a reminder, plus is this superposition state with an equal probability or amplitude for 0 and 1, but it has is a plus, those two. Minus is also a superposition between them, but with a minus sign here. So how do you think about this one? If your initial state is plus, here I show you this H gate on the left. You know that if your initial, if you had a 0, doing an H gate will give you a plus. If you had a 1, doing an H gate will give you a minus. And it's reversible. You can do this H gate apply to plus and 1, and you would reverse it back to 0. Plus and minus, you would reverse it back to 0 and 1. So then here, what you would do is to do a H gate, and then try to measure it. Now, this is true if the qubit has the plus state. So we need to make true if this measurement gives you 0 this time. So this should, 0. I can't spell. Yeah, so that's the logic. You already know, given this here, how you would change between 0, 1 and plus minus. Then you would just do a H gate to reverse it, and then do a measurement, knowing you will get either 0 or 1. Too bad my browser is not working, but copy this on your own computer. The task 1.4 also uses something that we learned last time. You are given an angle alpha, and you have two states. It's either A or B, and A is expressed as these cosine alpha plus sine alpha. B is minus sine alpha and cosine alpha. Very similar logic to the previous exercise, but now you are doing a rotation of your qubit. And we learned last class, if you look at these rotational gates, the Ry will be the one that would produce these two states. So now you need to reverse it from these states to 0 or 1, and then do a measurement. So what you would do is do a Ry, and then because alpha is what you have right now, and you reverse it, it would be just rotated back to minus alpha. Why is there a 2.0? Anyone remember? Last class, we have learned this about the Bloch sphere. And we know the relative locations, angles of theta and phi relative to these axes. So alpha is actually theta divided by 2. That's why we need to have this factor of 2 here. And then you do the same measurement. And again, true if is change from this state. So you do 0. So A will go back to 0 and B will go back to 1 if you do this. So that's the logic here for these exercises, is just letting you practice the measurement. And there's not much, not like the gates will have so many different kinds of gates. Measurement is very simple, just M, meaning measurement. And then you would get your states to wherever you want it to be, given any gates you apply to them. And the later exercises, you should do them. And we have certificates. Remember, the kata is a very good exercise for self-paced learning also. And for this one, measurement, it also has a workbook. If you get stuck, you can go look at it. But this, we don't have a workbook for all of the katas. This one is one that really teaches you, but there are later ones that doesn't have workbook, so you cannot look up on these explanations. This is a nice one. The later exercises are more, I would think, less to do with measurement, but more to do with how you write the logic, and it's mostly classical logic. So we would not work on it now, but definitely take a look at these yourself and also try other katas. And if you haven't done the basic gates, you should do that. So we are already at 9 o'clock. I just want to quickly show you a couple more slides that's related to the measurements. Okay, so the double-slit experiment is one of the examples, one of the experiments physicists in the early 1900s and later did to discover there's quantum effects. And there are a lot of other experiments that people did that really kind of lighting up the whole physics field, that there's something new that we didn't know about. So we'll not go through these experiments, but look them up yourself. All these effects that demonstrated quantization of energy, and they discovered wave-particle duality. Double-slit experiment was one of the experiments, and there were a lot of other evidence that they gathered through their experiments. That's what helped physicists realize the new fundamental effects that they didn't know about. And they also led to the mathematical description of the quantum mechanical systems. And Schrodinger's equation was then invented or derived to explain these effects that they observed. So Schrodinger's equation, if you look at the form here, it looks like a wave equation. It's got this delta derivative of function here, and then it's got a time derivative of the same function. And this here, V here, is just an external potential. Sometimes you don't have this term here, but if you just look at the form, it looks like a wave equation. And then they must have wave solutions, as or called wave functions. The derivation led us to know that the solutions would be a linear combination or superposition of all of the possible wave functions. So very rigorously, you can derive this result out. And that's why in quantum computing, we're using the fact that you can have two, or if you have one qubit, you can have two different possible states in superposition. Whereas in nature, you can have all those infinite number of possible wave functions in superposition. So in quantum computing, we're basically just using two states to be our units, to be our basis for computation purposes. And Dirac comes along and try to simplify things because wave function can be really long, and you can write these amplitudes in terms of the overlap between these this one possible outcome with the overall wave function. And then that's how you can calculate what the amplitude would be. And Dirac came up with a simple notation called Dirac notation that would just be shorthands of these integrals. This is the overlap integral between this one of the solutions with all of the solutions. That's why we have been using this symbol. I didn't really introduce at the very beginning, but now we know. I was just using them as symbols and it didn't stop you from understanding. But now we know where it comes from. This is a shorthand for wave functions. This has a name. This is called a kit, which is a second half of the bracket notation. So this part is called a bra. But what it is a complex conjugate of the wave function. So for physicists or for people who have learned physics, you have seen this. And this is how you would do an overlap integral to shorthand this mathematics. And for people who have seen the hardware class that I've given, I have showed some parallel comparison between many different systems in our universe that actually behave very similarly. So people who have seen this commented last time that this was very beautiful. So this now today we have more examples. So this is showing the Hamiltonian of all these different systems, pendulum, weight on the spring, or LC circuits. This is a superconducting LC circuit, which is used as a unit for possible kind of qubits, also experimentally. We also have nucleus. If you look at their energy or Hamiltonian, they are kinetic energy plus potential energy, and they have terms that have very similar mathematical looks. So learning physics is basically learning all these systems as a model, and you will see how similar different systems are. And the similarity with wave equations, what led physicists early, like 100 years ago, was they measured particles and found they look like waves, and measured waves and found they look like particles. And that's why they could write things in terms of wave equations, and which is Schrodinger's equation, and then they figure out the solution must have or be wave functions. But before this class, we've already been doing quantum computing. We've been doing gates and vectors and all that. We did not need to use any of these. In a way, we are figuring out the best way to teach people about quantum computing. We don't even have to go to physics. So you don't have to know a lot about physics to start working on quantum computing. But it's still very beautiful to show you that they all have physical roots. And if you look at classical waves, they have this wave equation. You can figure out what the velocity of your propagating wave is from just by looking at the wave equation. So in parallel, we have electromagnetic waves, which are light. And electric field and magnetic field, you can also express these. And these are derived from Maxwell's equation. By the way, yesterday was Maxwell's birthday. And these are the 4 Maxwell equations. If you rearrange them, you get to this wave equations. And then you look at quantum waves, these are Schrodinger equations. So they have very similar, they're basically all wave equations. And then you can figure out the wave velocity. And this is how Einstein got the inspiration when he looked at the Maxwell's equations mashed up into this wave form. He saw these constants here permittivity and permeability of vacuum and their constants. And he looked at the classical wave equations. This gives velocity. That means these two constants give you the speed of light in vacuum. That let him figure out the speed of light must be a universal constant, and which then also led him to develop relativity. So this is what's really beautiful, to look at history and how physics was developed, and how just by looking at dimensions and units and equations, you can realize a lot of insights about nature. But again, you don't need any of this to do quantum computing, but I still like to show you. This is what you need to know about quantum computing, is that amplitudes can be negative or complex, and they can do distractive interference. Okay, so that's what I want to show you today. We have this survey on Microsoft Quantum Development Kit website, and this is really for you, an opportunity to let us know what are you looking for, why are you learning quantum computing, what do you want to learn next, so that we can develop official materials to provide you. Also, some really fun activities going on. Dr. Sarah Kaiser, by the way, I got these Q-sharp earrings from her. She's doing these live coding events on Wednesday and Saturday on her Twitch channel, so check them out. And we also have these coding contests going on right now. Register. There are already some sessions, like exercises posted, so you should take a look and have fun with it. And here are the links where you can find all of the information, and the class is recorded. You can find the past recording and slides on this link, and the videos are also posted on my YouTube. That's it. Any questions? Let me look at the chat here. People can also feel free to unmute themselves and ask.
Oh, hi, Kitty. Can you hear me?
Hi.
Yeah, hi.
Yes.
So, one of the thing I wanted to say was that there are a few experiments now that actually, on the quantum, even on a 2-bit quantum computer, that you can now fully reverse the original state in a superposition particle. One of them, so there's a retro reversibility.
Mm-hmm.
Also, there is this. I don't know if you saw the pool, billiards pool experiment. I'm sure you saw it.
Mm-hmm.
So, I mean, in terms of a full randomness of a quantum bit, because we are kind of looking at it from a superposition point of view, where does the Microsoft quantum randomness comes from, and how random it is?
I don't quite understand why you are saying the randomness is related to a company. So I don't know what do you mean by Microsoft?
Because this is a Q-sharp is a Microsoft version of
is the language, yes.
Yeah, and also, I mean, the Microsoft is investing its own quantum computing initiative, and this is different to, for example, Google working on it. Google, for example, works on the tunneling computers.
They use the superconducting circuits.
And similarly, IBM is using a different one. So I just wanted to know
superconducting circuits. Yeah.
Where does how random is the Microsoft version?
So, well, I don't know if you are asking about error correction or having intrinsic qubits going from one state to another.
And then
so I don't know how to answer that question. I don't really know. I don't think I fully understand your question and know the answer to that. But I think what could help is to look at the session I did on hardware, so different types of hardware and how they work. So intrinsically, these different Microsoft is using topological quantum qubits, and the language is not just specific to that. The language can be used to code any quantum computer. So the language Q-sharp can be used for superconducting circuits or trap irons,
So
or
let's say, for
any
example,
just yeah. So
le-
you have to compile from the bottom up how you change your qubits, and then write how do you translate that into your language.
so let's say, I use one of the, random quantum bits as a seed of something,
Mm-hmm.
and that then feeds
Mm-hmm.
into an algorithm, creates
Yeah.
a cryptographic construct. Now,
Mm-hmm.
because on a quantum qubit, 85% of the time you can
Mm-hmm.
reverse back to its original state.
Mm-hmm.
In a 3-state, it's even more. So my question is that how is it then becomes easier for somebody to then figure out the original state, and therefore it therefore it's no longer random. So I just wanted to understand the entropy uh, and the randomness of how, I mean, on what is the basis of that? You know what I mean?
Yeah, I kind of get what you're asking. I don't know the best way to answer that, but I think there's some concept mixed in this question right now. So there's the intrinsic errors of the hardware that you build.
That's correct.
So when you're doing a measurement, um, it could be messed up by any decoherence
Absolutely.
in the system. Yeah. So that's the error. That's the error part of the hardware. And I can only comment that the topological quantum qubits, this way that Microsoft is pursuing, is the least error prone. That's why Microsoft is pursuing that, because other types are noisier. So you can look up on papers on what's the order of magnitude, how quickly the qubits can collapse. But I think the question also has mixed in with the using that as cryptography
Seed.
seed. Yeah. So like random number generator, right? So
Kind of, yeah.
so you measure it many times and you get a series of random numbers. That I don't exactly know how the algorithm works, so I can't really comment on that. But I think I cannot comment on the how do you use it as a cryptography
No, no,
method.
that's okay because you don't know the
But I
algorithm. You
think
can't.
there's yet another concept you have in your question is reversing back to the original state.
Mhm.
So in Q-sharp, if you do more of these exercises later, you will see that there's a reset function where you just start. We always initialize our qubits to 0,
0-state, yeah.
and then you put them into different states using gates. And then when you do a reset, so you could do a measurement, but then when you do a reset, it always resets back to initial 0.
Mhm.
So there are ways to physically translate that into your hardware. But the middle layer, I'm not so familiar with. So I think in your question, there's these 3 things that you're asking about.
Okay, that's fine. Thank you for your help. Another thing, I mean, is there any chance you could describe the way in when, I mean, I understand that at the moment we're using a language construct, but in what way are the qubits actually? How are they actually quantum? In what way? I mean, in terms of actual hardware, not the
You should take,
not the
yeah,
Hadamard gate and all that, but
yeah,
in terms of actual hardware
qubits.
where the qubits are actually generated, the
Yeah.
photons. Can you describe it from a Microsoft point of
There's
view?
not necessarily photons involved. You should take a look at the, let me show you where to find it. If you go to the Hackaday project, in my own project, the Introduction to Quantum Computing, you would find class on hardware. So in this file section, go to view all 13 files. They have all labeled what the content is. Their session 6 is quantum hardware. So to take a look at that one is a high-level overview of all kinds of different types of hardware and which company is using what. So yeah, I think if people are interested, they can go back. I don't think I'm going to repeat that class, but this is recording. You should take a look. There are many, many different ways, and you don't have to limit your imagination of what to use as your qubits. So I think Barry has a question here saying, is reset Q the same as if measure Q equal to 1 and then do a flip Q? It's a very good question because I was trying to use the reset Q for that exercise too. It's not exactly the same. So reset makes sure, doesn't matter what your outcome is, it just resets it to initial value. Whereas this exercise is specifically asking you to know the 0 and 1, like literally thinking your outcome as 0 and 1. But the reset is more like erase everything and reset. Any other, let's see, any other questions in the message? Yeah, thanks, Anna. Yeah, thanks, Isho. Glad to see the hardware class was helpful. Taro comments, Q# is a language that interfaces with and uses simulation software. It is not connecting to actual hardware quantum computer. No, actually, we do connect it to actual hardware. Right now, because, well, during the development, because when we didn't have hardware, we had to use simulators. So Q# definitely can be used for simulation. And in fact, these katas were using simulators, but we do connect to actual hardware. And the newly announced Azure Quantum service is a cloud service that connects you through your own computer writing Q# to a hardware system sitting on the cloud. So currently we have Honeywell, IonQ, iQubit onboarded onto Azure Quantum. IonQ and Honeywell are using trapped ions, and 1QBit is using superconducting circuits. So Q# again can be used for, it's a general language and it can be used for any hardware. You just have to have a translation layer that translates your quantum program to how they actually manipulate the qubits, like using lasers or applying different voltages, things like that. All right, thanks everyone. I think we're gonna stop here today. See you next class. Thanks, Michael.